there is a small issue with the last class recording, video recording, guys. I'm trying to fix it. And, because my laptop memory was full, so it did not record it properly. It is asking me to, download something like this. So I'm trying to fix it. And inshallah, once I finish it, I will upload it. Okay, now I have cleared the memory. So for this class, we shouldn't get any issue. Okay, so let's get back. And one more thing. Yeah, so tomorrow, I don't know whether you have received the email from the EE Club or not. Have you guys received?
It's the tutorial, right?
Yeah, the tutorial, yes. Yes.
Yes, we received from you and from the department.
Okay, so from me, I have already posted here because I have seen the comments on my Google form that many students are saying that we do not have enough number of questions to solve, So that's why I thought of just having a separate tutorial where we will solve the problems, but this is optional, guys. Okay, this is optional. That's why I have bolded. It's an optional. You are not forced to attend. So you can join and we will try to solve a few examples from the electrostatic material. Okay. So let's go back. So today we are going to finish the Ampere's law, and we will take the magnetic flux density. So if you remember, we were doing the Ampere's law, and we took an example of non-negligible thickness wire, this one, and how to solve for the magnetic field which is created by the current which is flowing in this wire. And then for the coaxial cable, I left it to you because you can go through this example. The solution is already here and try to understand, and I'm here anytime. If you have any doubt, you can send an email to me, or you can come during the office hours and I can explain this to you. Okay, so we were looking at the toroid, and I explained what is the toroid, how does toroid looks like, and we were trying to find the field, the electric field of the toroid. So how does the electric field of the toroid looks like? So if you see here, this is my toroid and this is my wires. So, if you see from the back side, okay, so let me just turn. So this is how the wires will be at the back side, and this is the front one. And the direction of the current is in this way. So the wire is wounded, and this is how the current is flowing in the wires. Okay, the current is flowing in the wires. And this wire is wounded on a circular cross-section ring. See here, this is the circular cross-section ring of diameter 2a, and rho 0 is the distance between the center of this cross-section to the origin. Okay, so which coordinate system I have used? I have used the cylindrical coordinate system. As you can see, it's cylindrical coordinate system where my z-axis is coming out of my screen. See, this is my z-axis. It's a dot. So coming, it is out of the screen, and this is rho direction. So therefore, this is the rho 0, and this dotted circle is referring to the center of this cross section. Okay, now how the field looks like. Now I want you all to take your right hand, and then you use your right hand and try to put your fingers, 4 fingers, in the direction of the current, and then the thumb will give you the direction of the electric field. So if I put my hands in this direction, because the current is going in this direction, remember, it is in this direction. So if my curving of my hands are like this, then my thumb will be like this, right? Because if this is my curving of fingers. So my thumb is going upwards. And as you move your hand like this around the circle, so what you will see, the electric field is in which direction? The electric field, how does the electric field looks like? Yes. So the electric field is going, oh, sorry. This is very light color. Let me make it a dark. So the electric field is going in this direction, like this. See, this is how the electric field is going. And so so all of you, you got this, right? Did you get the electric field direction? Did you put your hands and
Yes.
see it?
Yes, doctor.
So the electric field will be in this direction. And so therefore, what in our cylindrical coordinate system, so it will be in which direction? Will it be in rho direction, phi direction, or z direction? Which direction it will be? Which direction is
Phi.
phi? So this is the phi direction. So this is your a phi direction. So that's why my magnetic field will have the phi direction. So therefore it will have only h phi component. Okay, so this is from our, a little bit of experience. Now let's go. So now we need to apply the Ampere's law. So let me erase this. So now first we apply the Ampere's law. Now we have to apply the Ampere's law first here. That means I'm applying in this region. See, this region where my rho is between 0 and rho 0 minus a. So rho 0, this is from here to here is rho 0. Minus a is this. So in this region. So how do I apply in this region? I first put an Ampere in the path. So put an Ampere in path. So this is the Ampere in path. And this Ampere in path has a radius of rho. Now you apply the Ampere's law here. So what does the Ampere's law states? So the Ampere's law states that closed line integral h bar dot dl bar is equal to the current enclosed. Now can anybody tell me what is the current enclosed inside this green circle? Yes, Mr. Taha, Mr. Taha Al-Kazim, are you here?
Yes.
Yeah,
Yes.
can you tell me what is the current inside this green circle? Is there any current inside the green circle?
No.
No, because all your currents are flowing here,
Current is
right? So nothing
no.
is there. So that's why this is equal to
Yes.
0. And therefore, we conclude that the magnetic field is equal to 0 in this region where rho is between 0 and rho 0 minus a. Clear? Now,
Doctor, what is A?
a is the radius of this core. See here? Did you get it?
Yes, yes.
So it's the radius of this core because our core cross section is circular. So it's the radius of that core. Okay. So now we are going into the second part. So therefore my magnetic field is 0 here. Now what about my magnetic field in the core? So if you see here, what is the magnetic field in the core? So now I'm here. So this is my center. And now my rho is between rho 0 minus a and rho 0 plus a. So if this is my rho 0, sorry. So if this is my rho 0, which is only till here, this is my rho 0. Then what will be this one? This will be rho 0 minus A. And what will be this one? It will be rho 0 plus A. That means I am in this region. Can you see this one? This region, which is the core region. It is the core region. So I'm looking at the core region now. Okay? I'm looking at the core region. So in this case, what will happen? So let's go upstairs and let's see here. Yes, what will happen here in this case? So closed, let me change it. So closed line integral h bar dot dl bar is equal to the I enclosed. Now we are in this region, right? We are in this region. Now, can you think and tell me what is the current which is in this region? Because my Ampere in loop, so where is my Ampere in loop? I am putting my Ampere in loop here. Can you see this? This is my Ampere in loop, because now I need to find the magnetic field in the core region. So therefore, I'm putting the Ampere in loop in the core region. Okay, now I need to find the current enclosed in this. So what is the current enclosed in this? Yes. Now, if you see here, this is the wire, right? And this is the current going out. So can I say that here, this is the wire and the current is coming out? And here also you have a wire. See, a wire. And now if I cut my wire here, how will be the current? The current will be coming out. And here also, if I cut the wire, the current will be coming out. So the current will be something like this. Understand? Yes?
Yes.
Yeah. So what I am doing is, to this core, this wire is coming out like this. So now I'm now cutting this wire here and I'm trying to see how that wire looks like here. And I saw that the wire will be something like this. And then it will coming out of your screen and going to the other end of the core. So like this, you know, how many windings you have? You have n windings. So you have n windings or n turns. You have n windings. So that means, you know, how many of these currents you will have here? Because each winding is carrying current I. So you have n windings. So n windings will carry how much current? Yes? N times I. So because all these currents are inside my violet Ampere in loop. See, they are all inside my Ampere in loop and they are coming out of the screen. And therefore the total current is, since if you have n number of turns, then you will have n number of currents. So that's why it is Ni. Okay. Now we know it very well. The direction of dl and the direction of h, they are the same. So this closed line integral, I can just replace it with h. Closed line integral dl is equal to Ni. And what is the length of this violet circle? The length of this violet circle is nothing but the circumference of the circle. 2 pi rho is equal to Ni, or your h is Ni over 2 pi rho. Or in terms of vector, h bar is Ni over 2 pi rho A phi. So this is the magnetic field when your rho is between, or when your rho is in the core. That means when I am inside this yellow region, which is the core. Okay, clear? So this is all for this region. Done? Now what about the outside region? So I also need now in this region, which is this region, outside. So the outside region. So in order to find for the outside region, what I'm going to do? Now I'm going to put my Ampere in path outside. So this is my Ampere in path outside. And now I'm going to apply my Ampere's law there. So this is the case where rho is greater than rho 0 plus A, right? Because this is my rho. And since this is rho 0, so from here to here is rho 0, and from here to here is A. So I'm going outside. So it is greater than rho 0 plus A. Now in this case, closed line integral h bar dot dl bar is equal to the current enclosed. Now can anybody tell me what will be the current enclosed now in this yellow loop? What will be the current enclosed? Maybe Basil, can you tell me? Basil, are you there?
Yes, Doctor. Can you?
Yes, Basil, can you tell me what will be the current enclosed here inside this purple, this purple color or violet color Ampere loop? Are you there, Basil, or no?
Yes, it's there.
Yeah. So now think about it. Just now we saw that if I cut the wire here, I'm seeing the current coming out. If I cut the wire here, I'm seeing the current coming out. So like this, you will have the currents coming out. See, they are all the currents which will be coming out. So how many currents are coming out? If there are n turns, then n times I is the current coming out. Is it enough? Or are there any other current which is going inside? Yes, are there any currents which are going inside? Yes.
At the outer edge.
Yes, so at the outer edge, if you see here, again, if you cut here, so what you will see? You will see that the current which is going into the screen, see, current going into the screen, current going into the screen. And how many of these you will see? Yes, how many of these you will see?
N.
N. So we will see N. So N currents are coming out and N currents are going in. And if this is the direction of my application of my Ampere loop, then the blues, according to the right hand rule, the blue will take the positive value and N will take the negative value. This is coming out, this is going in, and therefore it becomes 0. That means your H bar is also 0. So this tells us that your magnetic field is only, the magnetic field is only inside this core region. Neither it is existing here, nor it is existing here. So it is constrained within the core region, which is your toroid core region. And if you summarize that, this is your answer. See, so here also it is 0. So therefore your magnetic field is this one, which is only inside the core, and outside the core it is 0. Okay, so this is the toroid. This is the toroid. Now, we are just taking some special cases of toroid. What are the special cases of toroid? That if rho 0 becomes very much greater than A, what does that mean? That means your toroid, if this becomes very large and the diameter of your cross section is becoming very small. See, this rho 0 is becoming very large. That means your ring is now increasing and this diameter of the cross section is going down. Then in this case, what you can say in this case, can we say that, can we say this one, that is my rho, which is between rho 0 minus A and rho 0 plus A, because my rho 0 is very large compared to A, then can I say that this is nothing but this is simply rho 0? Because A is very small. A is very small, so it is rho 0. There is a typo error here, guys. So just remember. So it is rho 0. So therefore, in this case, my magnetic field will be Ni over 2 pi rho 0. So it will not be rho. That means under this condition, I can say that inside my core, so inside my core, so if this is my toroid, then what I'm saying is, if I'm here, this is the magnetic field, and if I'm here, this is the magnetic field. But what I'm saying that this magenta or pink color and the yellow color magnetic field will almost be the same. Why? Because this moving in this direction will not affect the magnetic field under this condition. That means the magnetic field, I can conclude that the magnetic field is now becoming uniform, is a constant. It's a constant. See, it's a constant. N is constant, I is constant, 2 pi rho 0. Everything is constant. But this is only under the condition that rho 0 is very much greater than A. Then we can conclude that inside the core, wherever you go, whether you go to the edges or you are being in the center or to the other edges, your magnetic field will be almost a constant. This is the first special case. And the second special case is if your rho 0 is tending to infinity. What does that mean? If your rho 0 is tending to infinity, that means your ring is becoming bigger and bigger, bigger and bigger, bigger and bigger, that if you start seeing by putting your eyes on this side, and if you start seeing putting your eyes on this side, you will just see like this, only see the core. And the turning of this core is at infinity. The turning of this one or the turning of this one is at minus infinity, and this is at plus infinity. So you are unable to see this. That means to you, if you are seeing here and here, you are just seeing a straight core. You are just seeing a straight core. This is only possible when I am making my rho 0 to go to infinity. That is, this rho 0 value, I am making it to go to infinity. Now, in this case, what will happen? In this case, if you see, you are making this tends to 0. You are making this going to 0. But we are doing under a condition, because rho 0 is here. Can you see this? So if this is tending to infinity, then your magnetic field can become 0. But you can do it in such a way that you can do it in such a way that this term is finite. That means if this is tending to infinity, we will select n. We will select n in such a way that this term becomes finite. And this term is called as the turn density. It is called as the turn density. So n is equal to capital N over 2 pi rho 0. This is called as turn density in the case of toroid. Turn density. That is the number of turns divided by the, yes, what is this 2 pi rho 0? Is nothing but the circumference of your toroid, or I can say the length of your toroid. So this is called as turn density. And then, therefore, your h bar will become just this one. So h bar will become, so this is replaced with small n, and current I is as it is. And now this is your magnetic field. And since now it has become straight, then we do not require to write a phi. Suppose if it is in along the z-axis, then it becomes a z. And this is nothing but a solenoid. So a special case of toroid is a solenoid. A special case of toroid is a solenoid, which is your next example. So you can derive the expression for the solenoid by using the expression of toroid and assuming that this is the special case of toroid. You can get this expression, or you can do it in this manner. So what is actually a solenoid? A solenoid is very similar to your toroid, except that, you know, it is wounded. See, the wire is wounded in a straight horizontal direction. And it can be wounded on some material like this. So this can be wounded on some material like this. And this material is our core material. Very similar to your toroid. Got it? And now if we go and look at it, how the field of toroid looks like. So what you can do is, we can assume that this is my solenoid. Okay. And I've played around x-axis, and n is the turn density. So in turn density, if it becomes straight, then the turn density is nothing but number of turns divided by the length. What is your length of your solenoid? This L. That is called as the turn density. But the expression will be the same that we got it for the special case from toroid, which is Ni. And if it is in the x direction, it is Ni AX. This is called as the solenoid. And remember one thing, the expression that we got, this expression is valid for an infinite length solenoid. So what do you mean by infinite length solenoid? Because we got this from the special case of toroid. That means I'm not able to see the edges. So for the solenoid also, I'm unable to see these edges. Then it is called as an infinite solenoid. Why? Because for the infinite solenoid, this expression holds. That means whether you are at the center of the core, or whether you are at the edge, or whether you are here, or whether you are here, or whether you are here, your magnetic field is a constant. That is, the magnetic field is uniform. And this is only possible when your solenoid is of infinite length. Of course, you know, this is for the simplification purpose, but in reality, that is not the case. Because in reality, if you see here, the solenoid, how it looks like, the edges are there. So in this region, if you see here, the field is almost constant. The field is not changing. Now it is only changing in these regions, which are nothing but your fringes. Here also your fringes. So the expression of H bar, which is Ni times Az, this will hold only in this region. But as you go in this region and this region, it will not hold. So what we do is we are using the simplified equation for our course, but in the lab you will see, that how this expression will hold. You will see that this expression will hold only at the center. And as you go on this side and this side, this expression will fail. And in the lab, we also have the expression for a finite solenoid, which is a large expression. It's a complicated expression, but that is out of the scope of our lecture. So there you are going to only use that expression to check. But in our course, we are only going to use this uniform expression. Okay, so this is your solenoid. Now, how to get this expression again? You can do the following. You can go through this example, and this example will take you how to get the expression of a solenoid by using Ampere's law. But in the end, you will see that here also you will get it as Ni. See, you will get it as Ni on, and your H will be Ni times Ax. So this is by applying Ampere's law. And here we were able to get it from the special case of toroid. Okay, guys. So this example, I am leaving it to you. So you can do it. You can go through it at home. So this is the toroid and the solenoid, very commonly used inductors in the 80s and early 90s. And now how the electric field of them looks like, of the toroid and solenoid, this is how the field looks like. So as I have told you, that this is a very good website which will allow you to visualize everything. So go to the magnetic applet, and then here you can go and look at the toroid. So, and then if you go and look at the field vectors, see, this is how it looks like. So within the core, it is going in this clockwise direction, and this direction is decided by the flow of the current. So how the current is flowing. So the current is flowing in this direction. That's why. And if you want to see the lines, this is how the lines looks like. See here? So vectors. So if you want to increase, you can decrease the radius so that you can see it properly, and increase the center radius, increase the number of turns, increase the density, and now see here how it looks like. See,
Doctor, reduce the number of turns. It will be more clear.
I think the number of turns are very high, and let me also reduce the turn density also. So now it will be easier for you to see. Okay, so it is going in this direction. Okay, now for your solenoid, this is how it looks like, solenoid. Oh, sorry. I am using it is not field vector. Sorry, it's this field vector. Yeah, that's why I see this is the solenoid. If you see here, so let me make it properly. Sometimes it gives tough time. Yes. So if you see here, inside it's almost, so if I increase the inside, it is almost constant, but outside it is going out. So here are the field fringes. Here are the field fringes. And let me reduce the diameter also. So if you see the diameter, forget about this white arrows and increase the number of turns. This is how it looks like. See? So inside it's almost constant, but outside it is going like this and then returning back. Going like this and returning back. Here also going out and returning back. Going out and returning back. And for the toroid also, I think we did a mistake. For toroid also, yeah, we have to look at the field vector. So this is the field vector. We were looking at field vector A. That's why it was confusing. Sorry. So you have to look at field vector. So if you see the field vector, it's all going in the A phi direction. And it is concentrated inside the toroid. You can reduce the center radius. See here, it is okay. So it all again changed. Let me go back now. So the white and green got mixed up. That's why. But you have just now seen it for the solenoid. Yeah. So actually they are mixed up. I don't want to mix them. Yeah, the white is coming. I don't want the white to come. Okay, let me decrease the turn density. Okay, so this is better. And with the same thing, we will use for the toroid. Yeah. Okay. So the turn density was giving us a tough time. So this is how it looks like. They are all inside the toroid. Okay. So now let's go back. And this is how it looks like. See, this is how it looks like. So inside it was in the AX direction. If this is the AX direction, so inside it is uniform, but outside, if you are thinking about a finite solenoid where I can see the edges, then these are the field fringes and the field will go out and return back. Okay, so this is how the solenoid magnetic field looks. Now, before stopping our class, let me just define what is magnetic flux density. So the magnetic flux density is very similar to your electric flux density, where here we define it as B bar, which is flux per unit area, or its unit is Weber per meter square. Weber per meter square is the units of magnetic flux density. So therefore, the magnetic flux density is B bar, which is equal to mu times H, where mu is the permeability of the material. And this is again is related to the flux, but here it's magnetic flux, not the electric flux. Again, the flux, the magnetic flux is, so how much is the magnetic flux density crossing a particular surface? That is called as the magnetic flux. So it is integral over the surface B bar dot ds bar, and its units is Weber, and B bar is Weber per meter square. So here we are now introducing another property of a material, which is called as the permeability. And for free space, it is mu 0, and it is a measured quantity, which is 4 pi times 10 to the minus 7 Henry per meter. And similar to permittivity, here also you have a relative permittivity, relative permeability. And in electric case also we have relative permittivity. So here that is epsilon r, here it is mu r. So mu r is mu over mu naught, and mu naught is for the free space. So therefore mu r also takes a value, a constant value. And mu r, again, if you go back and look at the electrostatics, epsilon r is 1 over chi e. Here mu r is 1 over chi m. So where chi m is called as the magnetic susceptibility. Again, what is this magnetic susceptibility? That is how well your material can respond to the magnetic field, similar to how well your material can respond to the electric field, that is electric susceptibility, right? So now if I substitute this here, B is equal to mu H, which is mu R mu naught, and mu naught is like this, same, mu R is 1 plus chi m times H. And if I open this, so I will get mu naught H, and I will get one more term, which is chi m times H bar. And this chi m times H bar is called as the magnetic polarization density vector, similar to your electric polarization density vector. Okay, and this again, this is the vector which explains, how good is your material susceptible to the magnetic field, external magnetic field. Can it get magnetized? Can it not get magnetized? This is put under the umbrella of this vector. Okay, so for free space and for vacuum, or you know that our relative permeability will be 1. Okay, so we will stop, and in the next class we will take the magnetic vector potential. Okay.